All right, so up to now we've always dealt with frictionless items, frictionless pins, no friction contacts, things like that. So in this chapter we're going to introduce friction. So we're we're used to thinking about friction, or you should have been at least introduced to it in your Physics 1 class. And what we'll do is we'll think about we'll do sort of the classic. Hey, well that's apparently going to be green, I think. Color blindness is a problem. Block on a surface type of problem. So if I push with a force P on this block, it's initially, right, if this is on a rough surface here, not going to move. And in fact, what you can find is if you draw a graph of the applied load P as a function of time, so what you're going to do is you're just going to slowly increase P until finally the block moves, you'll get something like this. So a linear relationship as P increases, and then at some point the box slips and then slides. And so you have two regimes. You've got a static friction regime where the block is not moving. And so not moving. Oh no. And then a kinetic friction regime where the block is moving over here. And these are basically well, these are the two critical regimes for us in statics, right? So we're going to be asking specific questions about how much force is applied right before the block slips, which is this when the friction force P is at a maximum. All right, so the friction force is governed by two laws, typically known Coulomb's laws is one of the ways they're one. So in the not moving state, the friction force F is basically less than. Oops, hold on. Less than or equal to some sort of coefficient times the normal force. So if we draw the free body diagram of this block up here, we'll have our P, we'll have the normal force, the weight of the block, and then the friction force F, which tends to oppose the block's tendency to want to move to the right due to this applied force P. So this is not moving. And then when it's moving, the friction force is equal to a kinetic coefficient of friction times N. Note, this is an inequality, right? So the equality of mu s times n holds only at this point, right here, right before the block slips and starts moving. So the equality only holds at one point on this entire line. So that's a fine point, but one that will come into play when you're solving some problems on occasion. Then for the moving part of the kinetic friction, for if you're moving at a constant velocity, then or moving at all, velocity doesn't come into it. Then this is actually a constant, and this always holds. All right. Now notice one thing is coming into play here. There's no concept of contact area, right? So if this block, the fact that this block has some sort of length here doesn't matter. It's only the force, the normal force, right? The N, the effective pushing down on the surface that matters. All right. So you might ask yourself a little bit, or you might be curious to know, or curious about where this friction comes from, right? So everything has some amount of friction, and what happens is when you look at the interface of the block and the ground, so to speak. So if we were to take a picture of this surface right here, you could get pictures that look like this. So these are scanning electron microscope images of surfaces, some very highly polished. This is both of these right here would look like mirror finishes, and this one would be very close to a mirror finish. But you can see that they obviously have surface roughness still. Even this one, which has got extraordinarily fine polish on it. So here you have scanning electron microscope images, and so this is 20 microns. And here you have atomic force microscope scans. And so what this tells you, this basically is a 3D image topology image. So this is sort of like a topo map. So you can kind of identify, right? There's a deep scratch, and so there's that sort of deep scratch. And then here, this looks very smooth and non-scratchy, but if you look closely here, you can see there's a fine scratch pattern, and then this obviously is more rough, and you can see that in that place. And so this surface roughness is what actually generates the frictional force, or one of the things that generates the frictional force that's preventing this block from sliding to the right. Basically, what you get is, if you look in here, you will get this type of thing. So here's the surface roughness on one of the blocks, and then on the other surface, on the bottom surface, you get other surface roughness that has a tendency to lock in, right? So basically you get contact here, and contact here, and contact here. And it makes it difficult for this top surface here to move relative to this bottom surface. You have to pop it up over each one of these surface features. It's called asperities or roughness. There are also other mechanisms for friction known as non-covalent bonds. So non-covalent bonding, such as hydrogen bonding, this is basically intermolecular forces, van der Waals forces, and other sort of non-covalent bonding. So these are bonds where electrons are not shared. They're just either electrostatic, typically electrostatic interactions. So the fact that some molecules have charge. All right. So we've introduced a law for our friction, right? So let's bring back our two laws that we're going to use to calculate now that we've talked a little bit about our primary law. Now that we've talked a little bit about how or how friction comes about in real life. So we've got this Coulomb friction law, so this will give us this F. One thing we can notice though, right, is the frictional force F and the normal force are obviously related by the normal force, right? So the frictional force is just some coefficient multiplied by the normal, and the normal is just this. So what you can do is you can actually draw a sort of force triangle where here's our frictional force, here's our normal force, and then ask yourself, what is the resultant of those two forces? So the resultant R of the frictional force, the triangle that the frictional force and the normal force make, what is this resultant, and what angle theta does this act at? So this 90-degree angle will always hold, right? Because the friction is always perpendicular. The normal force is always perpendicular to the surface, and the friction is always parallel. So these two things will always be 90 degrees. And so we can ask ourselves, what's that angle? So we write tangent of theta, and then opposite over adjacent, so at mu s n over n. So we notice immediately, right, the n's cancel, and then the angle tangent theta is just equal to mu s. So this is called the angle of friction, and we can always use this relationship to figure out the angle that some sort of resultant, or that a frictional resultant is acting on a surface. So again, the frictional resultant is the result of the addition of the frictional force and the normal force. And that's pretty much it.